About a week after Swift was first announced, I wrote a blog post called "Swift is Not Functional." And we're about 2 years later now, and I'm here to tell you Swift is still not functional. So why are we doing here still talking about functional programming in Swift? It's really the wrong conversation. We're not going to be talking about functional programming in Swift. What we're going to talk about is the decades of experience and research that have gone into functional languages and that we can bring to Swift in our own Swifty way. So, what the heck is functional programming? Well, you all know it's, monads and functors and Haskell and elegant code. I hate to use this example because this actually is a perfectly good implementation of slice. There's nothing wrong with this code once you know how to read it. But look, I'm scaring you with Haskell. Haskell, be scared. Yeah, don't be scared. Functional programming is not a language. It is not a syntax. It is a way of thinking about problems. Functional programming was around for decades before we got to monads. Functional programming is a way of thinking about how you tear down problems and then put them back together in structured ways. Now, not everything we're going to talk about today is unique to functional programming. There's been research in this in other fields, but there has been stuff studied in that space for decades, so maybe we should learn something. Let's start with a simple example in Swift. We have this kind of code all the time. What do? It's a simple loop. It does two things. It converts names into persons, and then puts those onto an array if they're valid. Really simple, but there's actually a lot going on here. I mean, first, it converts a name into a person. And then if the person is valid, it appends it to the array. And of course, there's this whole iterating over the names loop thing, and there's a lot of actual stuff going on here. I'm counting 4 colors, right? The bigger thing is, in order to understand what's going on, you really need to execute this in your head. You need to be thinking, what does this array do, this person's array do over time, and kind of run it through and go, oh, at the end, this is what'll be in it. Nothing here actually says a list of valid persons with these names. So it looks simple, but it's actually a little complicated. How can we make things simpler? Well, we could separate the concerns. We could pull things apart. Remember I talked about pulling things apart? And if we separate the concerns, we now have 2 loops, and each loop does less. I'm counting 3 colors. I mean, baby steps, 4, 3, we're getting somewhere. Each one, though, again, is simple, and simpler code lets us find patterns. This pattern, create an array, loop over some values, do something to each value, and then at the end, put those onto another array. We do this a lot. Very common in almost every language. And when you have something that gets done a lot, you probably should extract a function. That's what we've always been learned to do. And of course, Swift has one. It's called map. And what map does is it converts a list of something into a list of something else. So that's pretty nice. Less code. We went down to 1 line of code. Fewer places for mistakes. We get to use a let rather than a var. It's all good, but the really important thing is that it says what it means. Whoops, come back. It says what it means. Possible persons is the mapping of names to person. It is a list of persons based on their names. We don't have to execute anything in our head. It's right there in the code, what we mean. And of course, the other loop, you might not be surprised, it also is a very, very common pattern. And it has a method, it's called filter. And filter takes a predicate. Predicate's just a function that returns a bool. And it applies it and gets us just the ones that are valid. So that's pretty nice. And we can put these together, and we can have possible persons and then tie them into our filter. And we've gone here from like 7 lines of code down to 2 lines of code, so that's pretty nice. We can recombine them. These are all values, so we can put them back together. Remember I said we tear things apart, put them back together? We put them together with chaining. So that's nice. We get this very easy, to me, very easy to read. I'll get to that in a second. But we can read it one line at a time. Names are mapped to persons, convert them to persons, filter out the ones that are invalid. That's nice. Now, I'll say this is not intuitive to read. If you have trouble with the syntax, that's no problem, I understand. But it is good to learn it and start to become comfortable with it. Because in my opinion, this is excellent Swift. This is how you should write it. You should not write the for loop in this case. I'm not saying the for loops are bad. For loops are great. But for this kind of code, this is how I believe you actually should do it. Because it tells us what persons is, rather than how to build it. And, of course, there's a ton of other functional tools. We've seen map and filter, and this big, giant, long list of tools. And these are all kind of things that we got from functional programming, and they're all kind of on collections, and it's great, it's great, it's great. You should definitely do all this stuff. That's not what I want to talk about today. These are tools. These are syntax. I need to show you a couple just so that we have somewhere to start. We're not here to talk about syntax. We're here to talk about thinking. In 1977, John Backus, who helped invent Fortran and Algol, wins the Turing Award. And when you win the Turing Award, they let you give a lecture. So this is his. Can programming be liberated from the von Neumann style, a functional style, and its algebra of programs? I love this title. I love the word liberated. So wonderful. By von Neumann style, he basically means Fortran and Algol. This paper was his apology for inventing them. And so what he would mean today is C. And what he means is imperative programming. The step-by-step mutation of some state until you get into the final state you want to be in. And when he says functional here, he doesn't actually mean what we mean by functional today, and whatever, it doesn't matter. But what is important is that at that point, despite the fact they didn't mean what anybody meant by functional, he inspired a lot of functional researchers to go and study stuff. And so there's this big boom in research in the late 70s because of this. This paper interested me a lot, though, for how we can take something back to Swift. And what it really talks about is how we can decompose complicated things into simple things, make those simple things generic, and then glue them back together using some rules. An algebra. Algebra is just a set of rules for putting things together, tearing them apart, and transforming them. And so we can come up with rules we could use to manipulate programs. And we already did that. We took a loop, we decomposed it into two simpler loops, found generic forms of each of them, and then put them back together using chaining. So when Haskell programmers come over, and basically any functional programmer comes over and they encounter Swift for the first time, they tend to get really frustrated, myself included. And it's because they try to do what you can do in Haskell. So in Haskell, the basic unit of composition in pretty much all functional languages is, wait for it, the function. It's right there in the name. It's why it's called functional programming. Because you can compose. There's beautiful ways like this to compose functions. I can create a new function, an entirely new function called sum, by gluing together the fold right function and the plus function and giving it an initial value of 0. And whether this is comfortable for you to read or not, once you do, this is actually quite beautiful. This is the kind of thing that Haskell programmers are going, I want to do this. Because I can just glue things together. It's beautiful. You can do this in Swift, but it's ugly, and it doesn't work well. And there's a reason. It's because you're working on the wrong unit of composition. Swift is not functional. The unit of composition in Swift is the type. Classes, structs, enums, protocols. These are all things that you can compose with. In functional languages, you compose with functions. In Swift, you compose with types. So this is a very, very common way to glue together two types. We have two types here. We have the sequence type, it's a protocol, and we have the mystruct type, it's a struct. And I can, by implementing one function, glue them together and have make a more powerful thing that now my struct has all of the methods of sequence. So that's the kind of thing we mean when we say we could compose things, we could we could build them up out of simpler pieces. And that's one kind of composition in Swift. Another kind that's very common is that we could lift a type into a context. Now, the most common form you're probably used to is optionals. So an optional is a type lifted into a context, and that context is maybe it has a value, maybe it doesn't. That's a little extra piece of information. You could have tracked it along with a bool, right? It's a little extra piece of information that goes along with the type. Does it exist? That's what context means. Now, adding context is much more powerful than other ways of tracking that extra information. So one way we could have tracked the fact that there is no integer, no value at all, is that we would have stolen one of the values out of integer, like -1. And we said it's magical. -1 means there is no value. But now you have to test that all over the place, and that's very ugly and very error-prone, and the compiler can't help you. But if we lift integers into an optional, all of a sudden the compiler can help you. It can say, hey, you have this context of does it exist, does it not exist? And I can help you make sure you don't forget about that that was one of the options. If you've ever used a -1 kind of thing, you know it's really easy to forget to check. And then all of a sudden your program goes crazy. That's, by the way, the problem with pointers having null pointers, right? Null pointer is I stole one of the legal values. I stole 0 and said this one's magical. It means no, the pointer points to nothing. And that's why we crash all the time, because we forget to check it. Let's build up a much more complicated example. So, a little more complete. So this is a very, very common API. I see this all the time. We have some function login. It takes a username and a password, and at some point is going to pass back something, a token, a string, something, and an error, possibly. I see this all the time, but I think we can do much, much, much better than this. We can do that by thinking about the contexts. So the first problem is this completion block. I say it's a string, but what is that string? Okay, it's a token. Okay, fine. I could throw a label on it. That doesn't really help us. In Swift, labels aren't part of the type. So I can have that or not have it, it doesn't matter. And even if I did, it still is this string thing. Well, strings are all kinds of stuff. I mean, anything can be a string. I mean, have you ever seen optional paren such and such show up in your string when you weren't expecting it? It's because anything can be turned in, can come over and become a string on you. Not just tokens. Tokens have rules. Maybe they have to be a fixed length. They can't be empty. You can't just slice out of them. That doesn't make any sense. Those are all things you can do with strings, but not with tokens. So we really want to lift token. We have more context about token. It has rules. We want to capture those rules. And we can do that. We can give it more structure. Structure. That's why it's called struct. So what do? I take my string and I throw it in a structure. This, by the way, doesn't cost anything. This doesn't cause indirection. It doesn't cause any extra memory usage. This costs the same amount of space as the underlying string. It's kind of cool in Swift, if you use a struct, not a class. But now I can put rules on this. I can say you could only construct these with certain kinds of strings. I could put extensions on it that would make no sense to stick on arbitrary strings. This is much nicer. And I can do this with all kinds of types. Strings, of course, but also dictionaries and arrays and ints. When you have these kinds of squishy types, you can lift them into a context and give them more structure and control what you can put onto them, control what they mean. Now, so if I swap that in, all of a sudden you'll notice this becomes self-documenting. I don't need labels. I don't need context. I don't need comments. It's clear that the first parameter is a token. Why? Because its type is token. Very easy. We like that. But still have problems. Second problem. We're passing a username and a password. And in most programs that have these, you always pass them together. Particularly the password is kind of useless by itself. It doesn't mean anything. So what you really want is a way to talk about a username and a password. I would like to create a rule that allows me to compose usernames and passwords with and. I need an and type. Well, we have one. It's struct again. And structs are and types. The credential is a username and a password. And the common name for and types is product type. And if you have a good struct, you can look at it, you go, a credential, just like that. And I encourage you to say this stuff out loud. A credential is a username and a password. Does it make sense? If it doesn't make sense, maybe it's the wrong type. Maybe you've built it wrong. And by the way, I know, functional programming, var, don't worry about it. This is a value type. Swift is not functional. It's fine. There's no shame in a well-chosen var. I absolve you. So that's pretty nice. So now we can swap in credential rather than username and password. It also makes our signature a little shorter, makes it a little clearer what we're doing. I like that. We also open up a lot of nice possibilities. We can do all this new stuff with, we could put extensions on credentials so that or we could swap in other types of rules for them. Maybe we want one-time passwords or access tokens or Facebook or Google or all these kind of things. That's really nice. And now I don't have to change any other part of the code because I'm just passing credentials. I'm not passing the bits and pieces that are inside. Still has problems, though. Still not happy. So we pass this tuple of maybe a token and maybe an error. I like calling optional is a lousy name. The right name is maybe. It is. It's maybe a token and maybe an error. You hear and again. It's because it's tuple. Tuples are and types. They're actually just anonymous structs. So just like a struct is an and type, so is a tuple. So is that what we mean? Do we mean maybe a token and maybe an error? I mean, there's 4 possibilities there, right? You got both or neither or one or the other. Only 2 of those possibilities actually make any sense, right? And so, OK, what do I do if I actually did get both a token and an error? Is that an error condition? Do I need a fatal error there? Do I need to ignore it? What do I need to do? You now need to really think about that. You probably need to write tests against it. The problem is you don't mean maybe anything. You mean a token or an error. Do we have an or type we can use? Of course we do. I wouldn't have asked. It's an enum. So in enums are or types. This or that structs are and types. This and that. And just like some are product types, some types are called or product types, and types are called product types. Or types are called sum types. That, by the way, makes perfect sense. Buy me a beer, I'll explain it. But for now, just remember, or, sum, product, and you're on your way to type theory. So we're going to build this little result type. And this really bothers me that it's not built into Swift, and there's lots of debates. This has been one of the biggest debated types out there because it should, but there's reasons they don't want to do it yet. And anyway, it's really easy to build, so we just build it. What we do is we're going to lift our value to give it more context. It goes from being just a value to being a successful value. And our error becomes a failing error. We get more context. And if we throw that resulting token, into our API, all of those impossible cases that we were having to write tests against, they all go away. Don't have to worry about them. They are impossible. And that's what I like. I want the bugs to be impossible rather than write test cases. So I actually kind of like this API. I log in with a credential, and it will give me back a resulting token. That's nice. I can just say it. That's the true legacy of functional programming. And that's the piece we should bring to Swift. Complicated things can be broken down into smaller, simpler things. We can find generic solutions for those simple things. And we can put those simple things back together using consistent rules that let us reason about our programs and lets the compiler make a lot of bugs simply impossible. And that's something I think that John Backus in the 70s and Krusty today would completely agree on. Break it down, build it up. Thank you.